Welcome everybody. Apologies again for the slight delay. My name's Sally Jordan. I'm the head of the Department of Physical Sciences here at the Open University. It gives me huge pleasure to welcome everyone, especially Anne, where have you gone? Okay, Anne Jones, and the rest of Barrie's family, I think, are sitting over there. And also to welcome Lisa, very special event. Of course, this is an event in memory of Professor Barrie Jones, who was a long-standing colleague and friend of very many of us who are here today. I actually have to start with two apologies, apart from the one for being slightly late. The first one is that you might have noticed that my name is not Anne Durrock, who was due to be giving this presentation. Unfortunately, Anne is off sick today, which is why it's fallen to me. However, I really am thrilled that it's fallen to me. I've got particularly fond memories of Barrie myself, which I'll say more about in a minute. The second thing I need to apologise for is that I'm not exactly dressed for the occasion. And this is because I was actually, until about half an hour ago, in the SS001 residential school lab here on campus, and I will, I'm afraid, have to dash back to that thereafter. That's actually a very poignant memory as well. The residential school that we're running now is a kind of reinvention of one that Barrie himself was involved with, as was Stuart sitting there. So it's a very, very special memory that's come as it has. So Barrie. Barrie, I believe, was appointed to the Open University in 1972, which was just 3 years after the Open University had first opened its doors to students. And in fact, he stayed at the Open University, living in Milton Keynes for the rest of his life as lecturer, senior lecturer, professor, and emeritus professor. He was notably chair of the first Open University astronomy module, S256, Matter in the Universe. He was an excellent teacher and greatly appreciated by his students. I think Anne, I think, is going to say more about Barrie the musician, but Yvonne, who I'm working with in the lab today, has remembered Barrie at residential school, his work. He was a musician, he would play the violin, the way in which he would link the experience of what he was doing to everyday experience and sort of therefore inspire students. The second thing I want to talk about, so that's Barrie the inspiring students. The second one is Barrie as a manager of staff. And this is where my own experience comes in. Barrie was appointed as head of what was the Department of Physics in 1999, a post which he held with great distinction for 3 years, and incidentally it was during that time that the Department of Physics became the Department of Physical Science, Department of Physics and Astronomy, which I think was due in very large part to Barrie's campaigning in that direction, and obviously the growth of our teaching of astronomy. Meanwhile, so back in 1999, at the Open University's regional centre in Cambridge, there was a tolerably competent but extremely nervous assistant staff tutor called Sally Jordan. And a post was advertised as staff tutor here. It was a staff tutor in physics and environmental science. Environmental science, I'm not really. But anyway, Barrie wrote a fairly interesting exercise. I had to write about the physics of rainfall. So I went through the interview process. The significant thing is that this post had a person specification with 17 points on it. Points 2 to 17 I had in buckets. Point 1 was have a higher degree in physics, which at the time I did not. And I am absolutely hugely grateful to that panel, including Barrie, for appointing me, and indeed for Barrie's mentoring, for the rest of his life. So therefore, what was the Department of Physics and Astronomy 5 years ago became the Department of Physical Sciences, and I now am head of that department. And so it's really, really makes me absolutely thrilled that it's me standing here now. Enough of me. Colleagues have also made some comments about Barrie's contributions. During his time at the Open University, Barrie inspired countless undergraduate students, particularly through the university's astronomy courses, which he played a major role in establishing in the early 1980s. At the same time, Barrie continued to carry out an astonishingly varied programme of research that included studies of alternative energy sources, such as solar energy, the cooling of infrared space observatories, and investigations of shallow bands, a rare phenomenon observed during total solar eclipses. Barrie's research into astrobiology began in earnest in the mid-1990s when he began to work with 2 PhD students on dynamical studies of the orbits of extraplanetary systems. Barrie pioneered research into the question of whether any of the newly discovered extraplanetary systems could host potentially habitable planets. Using dynamical methods, Barrie and his students investigated every system that had ever been discovered and published several highly cited papers showing how those systems in which Earth-like planets could survive for sufficiently long in the habitable zone of their host star to allow life to develop and thrive. Beyond his research achievements, Barrie was an excellent advocate for astronomical outreach. He gave regular talks to local astronomical societies, giving a great deal back to the amateur astronomical community from which he came. He was often interviewed for radio and television pieces and appeared on the Sky at Night twice, in 1973 talking about an eclipse of the sun in Africa, and again in 2004 talking about the search for planets around other stars. Barrie acted as the president of the Society for Popular Astronomy for a term between 2000 and 2002 and published several popular astronomy books, including Life in the Solar System and Beyond and The Search for Life Continued, Plants Around Other Stars, in which he used his inimitable and gentle style to communicate his passion and knowledge of astronomy to a gentler audience. It's a really good point, Barrie the communicator, it's great. Barrie was an active member of the national and international astronomical communities, organising several specialist discussion meetings of the RAS and serving as a member of their council for a number of years. He spent more than 20 years working in a leadership role within IAU Commission 46, Astronomy, Education and Development, including 3 years as Vice President. And finally, in recognition of his excellent astrobiological research, the Astrobiology Society of Britain awarded Barrie the David Wynne-Jones Memorial Prize in 2006, and he was a long-term member and ardent supporter of the Society and his goals. Again, very appropriate. So that's our memories of Barrie from here at the Open University, current staff at the Open University. I'm sure lots of you in the room could say a lot more. I'm absolutely delighted, Anne, that you're here. I'm going to hand over now to Anne Jones to say a few words. Thank you.
Well, it is a real pleasure for me to be here too, and I do thank all those who are here and those who are organising this on behalf of Barrie. Sally has given you a resume of Barrie's work at the Open University, but I thought I would tell you just briefly something of the other Barrie. Barrie, the amateur astronomer, musician, adventurer, and writer. So, as with many of us, Barrie's passions had their seeds in his childhood. When he was 8, his father took him to a talk at the local branch of the TOC-H. This was a club that I think was started for ex-servicemen and had its origins in the Great War. The talk was about the solar system, and Barrie says it was this that first fired his imagination. And from there he went on to make his own telescopes, spending his pocket money, buying mirrors and bits and pieces, and grinding his lenses at the kitchen table of their terraced house in the Welsh mining village until he was banished to his grandfather's shed in the garden. I think Barrie must have worked hard at primary school because he was only one of 2 boys in his class who actually gained a place from the 11 plus to go to grammar school. And it might have been the exciting opportunities and challenges of this new environment which may have contributed to some considerable backsliding in his first year. because when he took his school report home at the end of the summer term, he had come second to bottom in a class of 35. His mother was not pleased and sent him out in the garden to cut a switch from the hazel hedge. 3 swipes on the back of the knee, together with his parents' disappointment, and probably his own, taught him a lesson of a lifetime, which he never forgot. There were 2 teachers at his grammar school who also influenced his future. One was his maths teacher, who recognised his ability following that disastrous first year, and the other was his music teacher. Barrie did show an aptitude for music. His mother spent all her savings to buy him a violin, and I think it's the same violin that he has ever played. It was a very good one. He was selected to play in the National Youth Orchestra of Wales, but what he enjoyed even more was playing in small chamber groups. He would arrange and compose music to play together with various friends, and later with his brother, Nigel, and his 2 sons, our 2 sons. But at that time, a night out with the lads frequently involved the taking over of someone's sitting room. And the payback, for those who were banished to the kitchen, ranged from the beautiful rendering of a complete quartet to the experimental sounds of something very unpredictable, atonal, and somewhat hard on the ear. But experimenting wasn't just confined to the composition of notes. It also happened on sartorial lines, and some of you may remember Barrie coming to some of the first television programmes wearing this huge, chunky, thick sweater that his mother had knitted for him. But the story I'm going to tell you is when we recently had come to Cornell University in the USA, and Barrie had been invited to play second violin in a well-known chamber group playing at a concert at the Ithaca College of Performing Arts, which was just across the valley. So making what seemed a right assumption at the time, that being in America, being combined with it being an event at a local college of students, and it being in the early 70s, the appropriate dress would obviously be smart, casual, colourful. So we turned up at this fine theatre, and Barrie made his way to the artist's dressing room. You can guess what's coming. The lights dimmed, the audience were hushed, and the first violinist came onto the stage, gentle clapping, followed by Barrie, dressed in purple and blue plaid trousers, an orange shirt, and a bright floral tie. There was a deep intake of breath, and then the well-heeled audience burst into applause, which put everyone at their ease and made for a very relaxed and enjoyable concert. Another string to his musical bow, which Sally's referred to, was the playing of parlour music. The Walton Parlour Ensemble played at many a charity and OU event. And if you'd been at an OU summer school back in the 80s, you might have been serenaded by Barrie as a wild-haired, brightly attired gypsy playing Monty Chardas at speed as you queued for your refectory meal. And I think it's been commented that the entertainment was rather better than the food. When he arrived in the 6th form, Barrie was faced with a choice, either to follow the path of music or to go down the science route. In the end, the science route won, but performing and arranging music continued to be an engaging and social part of his life. At primary school, Barrie was known by his friends as Prof, not just because he wore those thick-rimmed National Health glasses that we used to get for free, but because he had the best ideas for games and adventures. And as you might expect from a gang of boys, their games did not always adhere to rules of health and safety, or indeed adult expectations of good behaviour. One of their games was to build dens out of the dry grass that grew down below the bankings near the river that ran below their valley. Then they would build these dens, and then they would set a match to them, crawl through, pretending to be firemen, and put the fires out. And talking with his brother, as far as we know, that they must have been successful, because there's no record of the real fire engines being called out. After several teenage pranks, including the mysterious appearance and subsequent disappearance of a road closed sign on top of a steeply pitched school roof, and a Free Wales slogan painted in huge white letters on a railway viaduct, in his adult years, Prof applied his skills to organising travel expeditions for his friends and family. But there's always some element of the unexpected in these trips. So it might be chasing a solar eclipse in Libya in the hands of some very gung-ho local drivers who really thought that the desert was their experimental driving ground, or navigating our way by compass in a clapped-out Land Cruiser across the Chalbi Desert, again before the days of GPS, or indeed camping on the edge of the Zimbabwean bush, trying to get that final photograph of Halley's Comet, aware of a gentle sound of purring in the undergrowth. Barrie always travelled light. Most of his luggage allowance was taken up with cameras, optical equipment, and a generous but always inaccessible first aid kit. And the legendary snake bite kit, a peace of mind insurance which fortunately was never required. I came across it the other day, well past its use-by date. See, I've got my pages mixed up here. Sorry about that. Barrie had a great gift for storytelling. When he wasn't employing this in writing units for OU courses or books for undergraduates, he turned his pen, and later his finger, because he's always a one-finger typist, to writing short stories for adults and children. His fiction style is something of a cross between Agatha Christie and Enid Blyton. Good, straightforward, exciting, page-turning adventures. He did self-publish 2 of his novels, but in his retirement, I think the real satisfaction for him came from the creative process. Barrie was an excellent teacher, enthusiastic, knowledgeable, yet able to explain things patiently at any level. My older son reminded me about what he called seminars with sausages. So over a family meal, a scientific or any question might come up, but a scientific one specifically. But you had to be aware of saying something casually like, I don't quite understand how, or why is it that? Because at that point, out would come all the post-it notes. Sorry about this. All the post-it notes and diagrams, numbers, graphs would be scribbled, accompanied by a clear, if somewhat lengthy, explanation. At the end of the meal, the person who would ask that fatal question would be told to take away the notes, get them in order, read them through, study them, and come back if they had any questions. I still have a set of these aid memoirs. It's to do with calculating the distances of planets and the nearest star that could be used for children out on a playground. So whether you were an undergraduate or an amateur astronomy club at an amateur astronomy club talk, or a Women's Institute meeting, or as a school child being fascinated by seeing the night sky for the first time through a telescope, Barrie could capture your imagination and expand your understanding. So it is very fitting that the legacy that Barrie left to the astronomy department should be used to continue this work of outreach and at the same time to acknowledge and honour other passionate communicators. And so Dr. Lisa Kaltenegger is one such person, and she is here with us this afternoon to deliver the first Barrie Jones Memorial Lecture. Thank you.
Well, good afternoon, everyone. My name is Terry Key. I am here representing the Astrobiology Society of Britain, for whom I'm extremely honoured to be their current president. And it is an enormous honour to be here today to present the inaugural Barrie Jones Memorial Award to our special guest, Lisa Kaltenegger. Just before I do that, I never met Barrie personally. I never knew him, but from what Anne has just told us, I'm absolutely sure that I've missed out on something special in not knowing Barrie. But it was clear that when we, a small group of us in the Astrobiology Society of Britain and at the Open University, and in particular I'd like to thank these 3 driving forces behind this inaugural Barrie Jones Award, that is Manish Patel, Stephen Sargent, and John T. Horner, who unfortunately can't be with us today because he's down under in Australia. It will probably be 1 o'clock or 2 o'clock in the morning for him. But he was the real driving force behind the establishment of this award. He knew Barrie, he respected him greatly, and he wanted us as a society to give something back in his memory. And it's taken a year or so to do that, with countless episodes of goodwill from many, many people in order for the Open University and the Astrobiology Society of Britain to come together, culminating in this day. So Lisa Kaltenegger, obviously her work, as we're going to hear about it very shortly, goes to the heart of some of the things that Barrie was very passionate about, exoplanetary research, but also her work on outreach and getting people interested in science is not just a reflection of Barrie Jones's legacy, but also that of Carl Sagan's. And of course, our guest today, Lisa, is the founder and director, the inaugural director of the Carl Sagan Institute in astronomy at Cornell. Lisa was born in Kuschel, I believe, in Austria, in the district of Salzburg, and trained as an astrophysicist before moving gradually through the ranks, doing her PhD, and then having joint appointments, I believe, at the Max Planck Institute for Astronomy in Heidelberg, and also the Harvard Smithsonian in Harvard University. Before thinking, I think she took up the position as the founder of the Carl Sagan Institute in 2014, I believe. It is our enormous honour and privilege, and mine in particular, to present the inaugural Barrie Jones Award to our special guest today, Professor Lisa Kaltenegger. Lisa, thank you very much. Oh, it's lovely. Thank you. I believe there will be photo opportunities will come later.
Perfect.
Well, it only remains for me now to introduce Lisa's presentation. Very briefly, I want to say just one other thing. I became a scientist because of Carl Sagan's Cosmos series in 1980. I don't know why I'm a chemist, but nevertheless, I'm a scientist. And it was really through his Spaceship of the Imagination, if you can remember that, as part of the Cosmos series, that really took me into different worlds. And I think we're going to be taken there today. Perhaps not on the Spaceship of the Imagination, but perhaps the Spaceship of Possibilities. So Lisa, I would ask on you to deliver your Barrie Jones Memorial Award lecture today, entitled Exploring Thousands of New Worlds, Finding Another Earth, and I particularly like the fact there's no question mark after it. Amazing.
Hello, and thank you very much for coming. It is my enormous pleasure to be here today. After everything I heard about Barrie, I also think I really missed out, not knowing him. But I think what I love about the description that Anne gave is that a lot of times scientists are portrayed as pretty boring and maybe only having science in their mind, but that's not the experience that I have with my colleagues. Usually they're very creative minds that do crazy things, and maybe I'm not exactly what you'd think is the norm person out there, but that makes your life a lot more colorful. And I think in a little bit by little bit, this is also starting to be more emanated into society, that this whole idea about scientists being in this ivory tower and not knowing anything, I think couldn't be more wrong in a way, because we are looking out and exploring the world around us. And so that is what I would like to take you on a journey on. What we're doing currently, and how incredibly exciting this search for other worlds is. When you talk to a room of people, and there's teenagers in the room, one thing that I always find very interesting is that none of the teenagers that you see have ever lived in a world where we didn't know that there were planets orbiting other stars. Because we found the first one orbiting another star about 20 years ago, 95, so 22 years nearly. So the worldview of a whole generation has changed already. They have never lived in a world where we didn't know that other planets exist. And what I want to show you today is what these planets are like, and also what's our next step in this exploration. Because now, after finding them, comes the next step of asking, what are they like? How can we explore them? They're very far away from us, orbiting another star. But the light travels through the universe for free. We can catch it in our telescopes, and thus we can actually read what's going on in the atmosphere of another planet, and I'll show you how. First, I of course want to introduce you to my amazing graphical skills, where I recolored our own Earth. What is actually making the point that when you think about another world, if you just change a little bit, like the temperature or the acidity, there might be other kind of life forms that could dominate that planet that we might have here in extreme environments, or they might be something that we can't even imagine yet. I'll bring you back to the point. But when I'm talking about finding another Earth, I'm not talking about finding us exactly at this point in time. I'm talking about finding another world that could sustain life as we know it. I love this picture because it basically shows a human reaching out to the stars. And that is what we're doing currently. We live in the generation where we're finding other worlds. So the next horizon is not the continent on the other side of the sea, but the next horizon is now those stars up there, those other worlds, those planets. And what we're really doing is we're making our first map of these other worlds. In the far, far future, very long in the future, not now, this could be one of the first maps people use for exploration to new targets far out in space. So what you see here is, of course, our own Milky Way. And I just want to orient you first where we are in the universe. So when you look up at the star at night, you see about 4,000 stars, roughly. But some of them are so close together, this is the white band here, where they're so close behind each other that you cannot resolve them. Thus, it generates the appearance of a white band in the sky. That is our Milky Way. So basically, how we look like from below. We are one normal star in the Milky Way. This is our sun on the left. Then we have 4 rocky planets. Then we have the asteroid belt. And then we have the 4 gaseous planets. And then we have planets like Pluto, Makemake, and Eris, so small snowballs. The further away from the sun you are, the colder it gets. It's like standing around a bonfire. If you're very close to it, it's hot. If you're very far away from it, it's cold. Of course, stars burn by nuclear fusion. They are not a fire at all. But the concept is the same. And so if you look at our own solar system, what you see is that the closest planets, we are the 3rd rock from the sun, 1, 2, 3, that's us. These are rocky and small. And the other ones further out are big and gaseous. Just because if you have materials, planets form in a disk of material of gas and ice and dust. If you're too close to the star, it will evaporate. All the ice will evaporate, all the gases will evaporate. The things you're left with are the rocks, and those rocks collide and making small rocky planets. If you're far enough away from this hot source, the star, then the cool things stick around. The ice is still there, the gas is still there, it didn't evaporate. So it can mix in when the planet is formed, therefore generating these huge planets. And they're basically completely different than the small planets we have closer to the star. If you had a huge, giant cosmic bathtub, you throw in the Earth will sink. You throw in Saturn, one of the gas planets, it will actually swim. If you need to do this at home or at a party, use a cork and a stone and a glass vase. If the communication died down, it's a little bit boring. Just say, solar system, always a winner. So this is where we live. We're living around a very, very normal star. And because I talked about a party or a kid's birthday, if you want to do that, you can actually make our solar system to scale very easily by just making a fruit salad. It breaks down a little bit, so you need a melon. Watermelon is Jupiter, then a large grapefruit, that would be Saturn. Uranus would be an apple in the scale, Neptune a lime. And then Earth and Venus would be a cherry tomato, so this is where your fruit salad becomes a little bit weird. Mars would be a blueberry, and Mercury in the same scale would be a peppercorn. You can also bring that out. You know, if you want to give somebody the solar system, that's a very healthy way to do that. But I was telling you that we see these stars and the night sky so close behind each other, what we call our Milky Way. This is because our Milky Way looks like this. Our galaxy looks like this. It is basically like a CD. That's how flat it is. In the middle, you could put a ping pong ball, and then you'd have the shape of our galaxy. All the things we see, the visible stuff, the stars. And so if you look outside of that plane of the Milky Way or of the CD, you see the individual stars. But if you look inside that plane, then you see them so close behind each other that they generate this white band that we call the Milky Way when we look up at the sky. It is roughly 100,000 light years across. So that means light actually needs 100,000 years to go from this side to this side. So if we were to find a planet all the way over there, we would see it right now as it was 100,000 years ago. The further away something is, it's like a light or a candle or a torch, the dimmer it is. Therefore, we really can't see the things 100,000 light years away. They are way too dim. We can't spot them. So we're really concentrating on the closest part around our solar system. So our sun is about halfway out from the center of the galaxy. This is the center of the galaxy. We are halfway out. And this is about 1,000 light years in scale. And that 1,000 light years is where we found most of the planets we have found so far. And we found more than 3,400 planets already. We know of thousands of other solar systems. And the interesting thing is there are really like nothing we expected. And that's, of course, the funny part about it. So I said when you look out of this plane of the galaxy, where you don't see this white stripe, you see the individual stars. But you also see a lot of dark patches in the sky. And the question was really, what is in these dark patches? Is there nothing? And so what the scientists with Hubble did is they basically used 200 hours of Hubble time to stare at one of these patches of dark. And when they did that, so they exposed for 200 hours in total, that's what they found. And this is, of course, the Hubble Deep Field image. But what it shows you is these dark pieces in the sky have or harbor thousands of galaxies. So in our own galaxy, we have billions of stars. And out there are billions of galaxies. Because everything you see here, if you take a grain of sand, outstretch your arm, put it toward the sky, that's the area that Hubble covered. There are a couple of thousand galaxies in that small spot. So there are numerous stars out there and numerous galaxies. And of course, now one of the questions becomes, how many planets are there? Well, let me come back to this. Our system has 8 planets. And our star is one of a couple of billion of stars in our galaxy. From everything that we found, I told you we found about 3,400 bona fide planets, and there are thousands more that we are vetting to not be an instrument error or something else. We figured out that every second star in the sky has at least one planet. I'm saying at least because it's really hard to find the smallest ones. So the numbers can only get better. The idea is that probably every star out there has its own solar system, its own planetary system around them. And we are just at the verge of finding them. But the distances, as I said before, are pretty vast. So if I take our whole solar system and in my mind I shrink it to the size of a cookie, then the next star in the same scale is 2 football fields away. And I apologize if somebody saw the game yesterday and didn't want to be reminded of soccer. My husband is Portuguese, so I had to vote for the other side. Anyway, so basically, this is our solar system. The next star is 2 soccer fields away. But the light from the star comes to us and we can catch it with our telescopes. And therefore, we can actually look at it and find planets. But if I don't go out of our solar system, we see these beautiful pictures of the Earth. I wrong colored it for you just to give you an idea how they could be different colors. But if we fly in our own solar system to about here, a little bit further out, and then we look back, that's what Voyager did. It's a small satellite that started in 1977, was launched in 1977, looked at Saturn, and when the mission was over, it was actually accelerated out of our own solar system. It's the only man-made object that left our own solar system in 2012. And on it, it has a beautiful golden record with recordings of some of the most beautiful music and other creative feats that humankind has done until then. And of course, Carl Sagan and Anne Druyan were 2 of the architects of what goes on this record. And one of the most beautiful things for me from this record is there is one song on it from an American musician that died in poverty. It's a jazz song. We don't even know where he was buried. He was blind and he died, nobody knows where. But his music just left our solar system and is on its way to the stars. That's what we can accomplish. And this is also, for me, a celebration of this human spirit, that we can send our most creative work out, maybe as a hello, maybe as a time capsule, because the distances are vast. For somebody to find it is going to be very unlikely. But we've made the first attempt. And just by reminding ourselves how many great things are going on the world, I think that's also a really good thing to do. To maybe concentrate a little bit more on the good things than the bad things. But I was talking about Voyager because before it left for the outer parts of our solar system, we're still in this cookie, it actually looked back at our own Earth, actually at all of the planets. And this is what it saw. And in case you're wondering, this is our own planet. This is the Earth. Seen from within this cookie. I haven't left our solar system yet. But of course, this is 1977 technology, right? Your digital cameras also got better with every year that you buy them. You wouldn't use one from 1977 anymore. But what it shows you is what we really see is this pale blue dot. And Carl Sagan wrote an amazing poem about this, about saying how this fraction of a pixel, this tiny dot, is extremely fragile. It is our home. And how ridiculous it really is that people fight so much about actually being able to dominate a fraction of a pale blue dot somewhere suspended in space. To me, this picture, when I first saw it, showed me how fragile our planet is. Because a lot of times when you get pictures of the Earth or when you walk outside, you just think nothing can go wrong. But once you change your perspective of seeing it from very far away, and as I said, it's not even that far away yet, you notice how fragile everything is that holds us together. And this search for life is an exciting endeavor, but it has a second component as well. The more planets we find like our own Earth, the more we'll understand how a planet like our own Earth actually works. And it can give us a potential or a view into our potential future. So the search for life and understanding how life works and the connection in the universe is one of the really exciting things. But it also will allow us to understand a planet much better. And this is the safeguarding aspect of this endeavor. And the way to phrase it, or one of the ways to phrase it, is think about it. If we find 5, 10, 100 on the Earth that are older than ours, and all of them, I'm making this up now, show a lot of sulfur in its atmosphere, sulfur dioxide, for example. We can't breathe that. That would be really bad. That doesn't mean that that will happen to our own Earth, that we'll have a lot of SO2 in our atmosphere. But it means it probably would be smart to develop a technology to filter out SO2 just in case this happens to all the Earth. This is what I mean with a potential future. And also, it will allow us to actually piece together the evolution of an Earth-like planet, from start to finish, as we can do with our sun. We know how our sun was born, and we know how our sun will die, because we find other suns at different ages, suns with different ages out there, and piece it together. But this was probably enough about our own solar system. I want to take you out now to the discoveries that have been made and to the future studies that we're doing right now. I find it really exciting to be born in the generation of explorers. I don't even have to go on a ship, what's also very good, because I wouldn't want to go for a couple of months on a spaceship. It would be pretty boring. Nothing said against people who want to go to Mars. If you want to go to Mars for a couple of months, go to Mars. But we're exploring these worlds without having to step foot on a ship, because the light from these thousands of worlds reaches us every day. And we can explore a planet just through the light, for starters, until somebody figures out how we get to the next star. And this is really how we find the planets. Most of the planets we don't see, but we see the effect that those planets have on their host star, on their sun. Because if you go for a walk in the park, right? If you see somebody walking like this, you don't need to see the dog. You know that somebody is like pulling it in that direction, and the guy or the girl really doesn't want to go, right? So you're basically balancing the draw of the dog by leaning back. In a way, very similar. The star, the gravity of the planet, tugs at the star, and the star leans back. And because they rotate, now this starts to look like this. So we can see the star going towards us and away from us, towards us and away from us, because of the tug from gravity from the unseen planet. And the more the star wobbles back and forth, the bigger the planet is, the more massive the planet is that orbits it. The less it wobbles, the less massive the planet is that orbits it. That's the radial velocity method, and how we found a little bit less than half of all the planets out there. But what this video also shows you is that if we are very lucky, I think this is annoying, sorry. Let's try this. So if we are very lucky, then by chance, the planet actually goes between our line of sight and the star. A star is incredibly hot, therefore it's incredibly bright. A planet is not. So if the planet blocks out part of this hot stellar disk from our view, the star appears less bright. And of course it does this periodically. When the Earth goes around the sun, once a year, our sun, seen from far away, would look a little bit less bright. When Jupiter does it, every 11 years, the sun will look a little less bright. And so this is how we can spot planets, and how we found more than half of them. That's what the NASA Kepler mission is doing, the 1-meter telescope who stared at 150,000 stars and found a couple of thousand, nearly 2,000 planets by today's count. But when the planet goes in front of the star, something else also happened that's really interesting. And this is shown here. So the planet goes in front of the star, and the brightness of the star dips, but part of the stellar light gets filtered through the planetary atmosphere. So the stellar light gets imprinted the information of what's going on in the atmosphere of the planet we see. And this is how we can tell you what is in the atmosphere of a planet very, very far away. And I'll get to that in a little bit in more detail. But if you do something, but now completely, okay. If you now say, how many planets are there? Big ones, small ones. Here I show you Jupiter. And then on the left, you see the Earth. The radius is on the bottom of this graph. This is one Earth's radii on the left, and it goes up to about 20. Jupiter sits at 11. And now, how many planets have we found? And what you see here is like not many for the giant planets. But we're finding more and more of the small planets. Now, something doesn't work here. And the something that doesn't work here is that with the wobble method, right, and also with the blocking out the starlight method, it's much, much easier to find the big and massive planets. For us to be picking up small planets in much bigger numbers, that means there must be so many more of those around. Because if you pick nearly all of the big planets up, but only, let's say, half of the small ones, but the half of the small ones is in numbers even more than all of the big ones, that just means there's so many more of the small ones. Well, for me, it's very exciting because I'm really interested in the small ones and the ones that potentially could be like another Earth. We have about 3,400 planets that we found. A couple of 3,000s are still being vetted. That is through the Kepler mission, for example, transits, where it blocks out the starlight, but also missions and searches from the ground in radial velocity, where it wobbles, or in transit. And one, of course, that the Open University and Britain generally is very heavily involved in. So if you want more details on how to find these planets, Carol, for example, can tell you all about it. I wanted to show you in a way that all of this, as you guessed, is not as easy. Because the star itself is not this nice, boring disk. But the star itself actually has a lot of storms going on. And then if you look very closely, these storms change that are different brightness patterns on the star. And here you see a planet, the size of a planet that we're trying to find, going across the star. So the planet is up here on the top third. And of course, we don't see any of the stars like that, except for our own. So what you're seeing here is Venus going across the surface of our own sun. This was the transit that just happened. But it shows you how difficult these measurements really are. But we can do this even though the star is very far away from us and only a tiny dot, and the planet is as small. The smallest ones we found are the size of Mars. We can't find all of those because it's incredibly hard to find them. But the technique is so sensitive that it allows us to, for the first time in human history, spot these worlds very far away. Now, this is a break in between. It's not art, even so it could be. Up here on the right corner is our own solar system with its innermost 4 planets. That's up on top, for you on the left. And this is just an overview of some of the planets we have found so far. There are big planets on the outside. There are small planets on the inside. There are small planets on the outside. There are big planets on the inside. And they're incredibly tightly packed systems. That means there are many more planets than there are in our own solar system in the space available. Why is that? Well, I told you before, one of the methods that we use is the wobble technique, right? And the other method is when the light from the star dims because of the planet going around it. Now, you want to find an Earth. You need a telescope for at least a year to stare at this star every night, right? usually telescope people really don't want to give you time for a year if you can tell them that you're going to find something, right? They're not very, very nice about that. In a way, they shouldn't be. And also for this wobbling, the faster the planet goes around the star, the more of a wobble you'll be able to detect. Plus, if you find the whole wobble in 3 days, you only have to look for 3 days. While if the wobble takes like a year to complete, you have to look for a year. Therefore, by definition, we find the close-in hot planets much faster. And we found many more of those. And this is what this ensemble shows. This is the Kepler. These are the Kepler planets. I just really like it because it just breaks with this idea that our system is the norm. And of course, the music is no Death Stars in here. But so, if you want to know whether or not our solar system is the norm, I cannot tell you yet. I actually don't know because we haven't found the equivalent to our solar system yet. Because for the Earth, you have to look for a year. For Jupiter, you have to look for 11 years. We have no data set that actually looks for 11 years at one star very frequently because the Earth takes 12 hours to cross the surface of the sun. So you have to stare you're not allowed to look away for 12 hours. If you look away for 12 hours, you might have missed it, making the whole point of looking at the star a little bit mute. So we don't know if our solar system is the norm. But what I can tell you is that not every solar system has to look like ours. We definitely know that. But one of the other things that's also interesting is that our sun is not the most common star. Smaller, cooler red stars are the most common stars. 75%, 3/4 of all the stars in the universe are actually not like our sun, but about only 1/10 of its size and much cooler. But that's actually a good thing in a way. Because I told you we look up at the sky and we see other stars. And I said that we can piece together the evolution of our own sun, how it was born and how it will die, because we look at other suns out there, older and younger than ours. So we know that our own sun will become brighter and bigger with age. Every star does. We also know that it was cooler and a little bit smaller when it was younger. And so all of that goes into what we call the liquid water zone or the habitable zone. At what distance from this bonfire or from the star do you have to be so that there can be liquid water on the surface of a planet? So why are we alive is another question to ask in the same context. Because we happen to be at this rock at the right distance from the star that's not too hot, that is not too cold, with liquid water, what we think we need to start life. Could also be subsurface, but we have nice liquid water everywhere on the surface. So we are within this habitable zone. This is the Earth. This is Mars. Key point, Mars is within the habitable zone. The problem is just that Mars is very small, not very heavy. So it can't really keep a lot of atmosphere around it. And if you just put the Earth here and don't put any greenhouse gases on it, we would be permanently frozen. The greenhouse gases in our atmosphere actually allow us to be above freezing. So greenhouse gases are not all bad. What we're doing is really bad because you really don't want to make it hotter and hotter. You don't want this zone to actually keep moving outwards because the planet won't. So you want to keep it nice and warm but not too hot. That would be good. But the key point being here is that only because a planet is in the habitable zone doesn't mean it has to have life. Mars is an example. And we really don't know what it takes to start life. That's one of the other really intriguing questions. But we said this was about now 4.6 billion years ago. But in the future, actually places like Jupiter and Saturn will become the nice habitable zone planets where there could be liquid water, where it's warm. While here around the Earth, it's going to be so hot that you're only going to have lava flowing. We have 4 billion years for that, so no worries. We have lots of time to get off of this planet. But we know that a star changes. Therefore, we know that a habitable position around the star is only a temporal thing. And I think it's pretty beautiful that being on this pale blue dot at a normal planet around a normal star, we actually figured out that in the end, we will have to get off it. That, I think, connects us beautifully to the universe around us. But I said, so now we found these planets. A lot of them are incredibly close to their star. Now, let me take you back to what I said before. There's the star. Then it's too hot, so you can only have rocks that mesh into each other, so you have rocky planets close by. And then further out, where it's cold enough, you have these big gaseous planets, because there's gas and ice when they were made. Now, the first planet we found, that I said every teenager lives in a time where we knew about exoplanets. They never lived in a time where they didn't know exoplanets were. That first planet couldn't exist. And it was probably really good that one of the discovery team, part of it was a PhD student. He didn't know that it couldn't exist. That helped in the discovery, I'm sure. Because we knew these gas giant planets had to be far out, right? We knew that Jupiter was the first one in our system. It's an 11-year orbit. So they finished making this instrument that can detect the wobble of a star. And they knew that they were only sensitive to big Jupiter planets. And so the professor, who's an amazing scientist, Michel Mayor, went on a sabbatical for half a year to Hawaii. Good call, he was in Switzerland. And the student, Didier Queloz, who's now at Cambridge, started measuring. And he had a signal within a week. Because the first planet we found is a planet as big as Jupiter, but it needs 4.5 days to orbit its star. So the year on that planet is from Monday morning to Friday afternoon. And as I said, and this is for all the young people and students in this room, sometimes it's really good if you don't know from all the literature and all the theory that something can't exist. Because it might exist and we just don't know about it yet. So keeping an open mind is one of the key things in research and what every scientist is trying to do. But so we find this planet. It's a tiny, tiny dot. And now I'm telling you, we're finding those even further away, over light years away, over cosmical football fields away. We can't see continents and oceans on it, but we can use the light of that planet. And that light of the planet, even so you don't see continents and oceans, is really a fingerprint that characterizes the environment of the planet and whether or not there's life. And scientifically, what we're looking for, when you look at the Earth, for example, you look at a combination of oxygen with a reducing gas like methane, because they react with each other and they would form, in this case, oxygen and methane, CO2 and water. But if you still see a lot of oxygen while methane is present that it reacts with, then something has to produce this oxygen in huge amounts. And if the planet is not too hot and not too cold, we only know for life to be able to do that. And so this is how we generate the fingerprint of life on another world. And you'd also like to have water because we don't know any life yet that doesn't use water. This is how it looks like scientifically. So basically, the light from the star hits the planetary atmospheres and gets filtered through the planetary atmosphere before it gets to us. And light is energy. If you go outside, hold your hand into the sun, you feel that it gets warm. And so the right energy hitting a molecule will start to make it rotate or swing or hit an electron in a higher stage of energy. And then when it comes to us, this filtered light from the star, that light is missing. So here you see you have less light at around 17 microns. That's the CO2 feature. 9.6 micron is ozone. It's characteristic what light is missing for the molecule it interacts with in an atmosphere. And so we can, over cosmic distances, read the composition of the air in another planet very precisely. We just have to gather enough light to do it. And I was saying, this might not be the planet. It might look different. It might have different colors. But the atmospheric makeup, so this tiny sliver of an atmosphere, it's comparable to an apple and the peel. The peel is really how thick the atmosphere is in comparison on our planet. That's what gives us a signal that tells us whether or not that planet can have life or is very different, like Venus, for example, where we don't have any ideas about life. So this spectral fingerprint, this light fingerprint, is really what lets us characterize the environment and the planet from very, very far away. Let me give you the difference. This is Earth's spectral fingerprint, the light fingerprint. You see water, missing energy here. You see CO2, missing energy here. Ozone, missing energy here. Water, and also CH4 here. Now, if you compare it to our own solar system, this is Venus, and this is Mars. And you only see features of CO2 in these planets. So these are the uninhabited planets versus the ones that are inhabited. That doesn't mean you couldn't have subsurface life, for example, on Mars, but it doesn't leave any telltale signs in the air of the planet, things that it breathes in and out that cannot be made geologically. And that's the only thing I can look for. Because life also makes CO2 or methane, but I can also make that geologically. So I can't tell apart which one is from life and which one is not. And I told you that our sun was cooler initially, right? Because like every star, the sun brightens. But that in turn also tells you that if our atmosphere wouldn't have changed through the geological times, the Earth would have been frozen solid for about 2 billion years. And this usually makes me come to very useful advice. If anybody ever comes and offers you a ride in a time machine, I usually ask my student what's the one thing they need to bring. Mind you, I'm now right now teaching in the US, so the answer is usually guns. And you know they can. That's natural selection at work. If you just bring a gun, you're going to open the door of your time machine and you're going to be dead. Because you can't breathe the air. What you need to bring, what would ruin every movie you see about time travel, is a huge mask, a gas mask that actually gives you the composition, 21% oxygen that we breathe. That's what you need to bring, the one thing. Then you can run away from dinosaurs or other things, but you need to bring your own air because the air on our planet changed. 4.6 billion years ago, our planet formed. Life started pretty soon after that. If this is a 24-hour clock, around 3 a.m. in the morning, life started. And around lunchtime, that's somewhere around here, oxygen actually started to build up in the atmosphere. The oldest fossils are around 9 p.m., and so on and so forth. Humans, last second before midnight. So if you want to go and find humans, you're looking at something very particular and an evolution that had to go the exact right way. And even if we have billions of planets, I don't know if we're going to recreate an exact analog of the Earth anywhere. But life, you can actually spot from the time that oxygen builds up in the atmosphere, because then you have the spectral fingerprint of oxygen with reducing gas. Now, turning it around, life existed all this time, but it produced CO2 and methane. Therefore, I can't tell it apart from non-life. So the environments were pretty different. This is what I was saying. You need a gas mask if you go with a time machine. And also life first started out as simple organisms, then became a little bit more complex, and then it became potentially intelligent. And all of that you can see in the spectral fingerprint and the light fingerprint from a planet, because the different mix of chemicals imprints itself on the light that gets all the way to your telescope. And so I was saying, our sun will do this in about 4 billion years. This is where you see the orbit of Mercury, Venus, and Earth. So our sun will become about 200 times bigger than it is currently. And at that point, the habitable zone will be out at Jupiter and Saturn. And it's kind of interesting because you can think about defreezing Europa and Enceladus and all of the icy moons, and there would be all of a sudden the really interesting planets out there. One last point I wanted to make, because we're talking about search for life in the universe, is that here I had colored these planets for you. But I've not just randomly colored that. I did, in a way, because I wanted to think about a planet a little bit different. But a lot of times questions come up as, what could life be like on another world? I don't know, because I would not have imagined the life that's even in the deep ocean that evolved on our own planet. And I just picked a random example because I think it's super cute. And this is another example that is astonishing. This is called a water bear or tardigrade, and it's about 0.5 millimeters, so it's tiny. Everyone in this room has stepped on one. But it doesn't matter because it survives pressure thousands times as much as the pressure on the surface of the Earth. And this tiny thing survives pretty much everything. You can cook it, you can freeze it, you can actually put it, leave it out in space without a spacesuit, and then after 10 days, they put it back in and put a little bit of water on it and happily crawled away and made babies and stuff. So the last talk I gave was with an astronaut and said, I'm sorry, but this is the guy we want for the missions. No life support, that's going to be fine. We don't know why it evolved the way it did, but it can sustain incredible feast of pressure, temperature, and other things, radiation, for example. And so I think our thinking is incredibly limited just by design, because I wouldn't have envisioned this organism existing. And if you just think that on another world, the conditions could be a little bit different, here's a picture of Yellowstone. You see the beautiful national park in the US. You see these beautiful colors, but those colors are actually organisms, biota, that live under different conditions in terms of temperature, in terms of acidity. So if a planet were just a little bit different, these organisms could actually be the dominant life form. And I can't tell you where it would evolve to, but one of the things I wanted to do is I wanted to also show you some of the resources we have. So we basically took, one of my students, Siddharth Hedge, took 137 biota from around the world, from extreme and non-extreme environments. And he said, if they were covering another planet, how would that planet look like? And this is what we call the catalog for the colors of life. Because snow algae, for example, it's called blood snow, could give an iced over world a red tint because it can live in ice. Algae bloom could give it a red or green tint. So just basically to break out a little bit of the box of thinking you would find green plants and animals and us. Because green plants, for example, have only been around for about roughly 500 million to 750 million years on this Earth. So these planets that we're finding, by definition, will be fascinating and new. And I wanted to share with you how an idea came to life. Because, as you heard, I'm the director of the Carl Sagan Institute at Cornell. And really, when I was thinking about exoplanets, what I was thinking about is that we need to look at this question from many different angles. A biologist is trained completely differently than a physicist, than an engineer. And so bringing everybody in the room will actually get you to ask the right questions and have some answers that are not the standard answers that you would assume. And so what we did at Cornell, and this was with the help of Anne Druin, who's the writer and producer of Cosmos, is we actually made that idea into reality that we call the Carl Sagan Institute. So the start is the image that you had seen before. But now, in addition to that image, we have these other worlds on our horizon. These new worlds that we just spotted, but we really haven't figured out whether they have life or what kind of life form they would have. What you see here is that our own planet has a human fingerprint on it, because right now we are the dominant species on our planet. But the other planets really do not, because we're just at the cusp of finding out if they could have life, and if so, what kind of life they would have. And so, with that, I would like to go back to our exploration. We're reaching out to the stars. We're reaching out to these new worlds. We have discovered them. We still keep discovering them. The most exciting ones for me are the small ones. And really, we are living in the time where we get to figure out whether or not these planets are anything like us or not. Making this map of targets for future discoveries. And you might know there's the first ideas around about going to the next stars, the Starshot initiative by Yuri Milner in the US, trying to get with 20% the speed of light with tiny, tiny chips to the next solar system and trying to take an image of those planets. And whether or not that approach will work, only time will tell. But I find it is amazing that we're living in the time where we can actually talk about potentially going to another star in the future without everybody laughing or wanting a glass of wine. We are living in this amazing time where we're basically finding complete other worlds out there. And they will also help us figure out how to safeguard our own planet in the future. That's one of the first things we want to use this for. Oops, and now it died. Account name, okay. But so, I want to go back to this first slide. And yes, I didn't put a question mark, whether or not that's good or bad. We don't know how widespread life is. We have no idea. It could be everywhere. It could be extremely rare. If it's extremely rare, we need to build bigger telescope. If it's widespread, in a year or two, when the next telescope after Hubble, the James Webb Space Telescope, that's 6.5 meters in diameter, goes up into space. It's about 4 times me in diameter. Then we have the first shot to have a look of whether or not such fingerprints of life exist around the stars, or in planets around the closest stars to our sun. Again, they want to be as close as humanly possible so we get as much light as we can. And we're building another telescope that's 40 meters on the ground in Chile. That will come online in 2022. If life is widespread, we'll figure it out pretty soon. If it's not, we'll build the next generation of telescope to collect more light. But just to live in a time where the technology actually exists to find these worlds, but to also read their air and figure out what the environment is like and whether or not there are signs of life on it, I think is pretty special. And with that, any good ideas you have about how we could find things better? This is for everybody in the audience. Outside of the box thinking, strange worlds out there, but we're getting the technology ready to actually characterize them. And with that, to all the explorers in the room, thank you very much.
So I think it falls to me to chair the last part, which is a Q&A. So Lisa has kindly agreed to take some questions. And I believe we have some roving microphones. So would anyone like to ask Lisa a question?
Hi, Lisa. Fabulous presentation. Thank you very much. You touched on it briefly there, that maybe some of the moons, some of the icy moons might become quite an interesting place or quite a habitable place, perhaps. Now, given there's 8 planets in our solar system, but considerably more moons, is it actually perhaps exomoons that we should be getting excited about as being potentially habitable worlds?
Absolutely. I'm getting excited about everything that could potentially be habitable. But the key point is, if you do the wobble, or if you do the transit, a moon is even harder to spot than the planetary body it orbits. And so far, we haven't found any moons around planets that don't orbit our own sun. We suspect they're there. Looking at our own solar system, we have hundreds of them. So, this is only going to get better if there are moons that could be habitable, because you could even invoke, there's a big, giant planet at the right distance. That one is not going to be interesting for life. But if it had a moon the size of the Earth, that one could be incredibly interesting for life. So basically, it's a bit observation-driven. What we can find is the one that we basically want to prioritize and focus our telescopes on. And then there's going to be so many things we can envision that might be even more exciting that we just can't find yet. And the second point that I wanted to mention is I talked about this habitable zone where there's liquid water. In our own solar system and anywhere else, life could start subsurface. We're thinking about the moons of Europa and Enceladus, these icy moons that have oceans below the ice crust, and then there could be life there. And I'm not discarding that at all for other systems. So, it's not just the planets that we found. I should have actually said that. So every fifth star has a planet that is the right size and at the right distance, not too hot and not too cold, that it could potentially be like the Earth. We have 1 billion of stars in our own universe, in our own galaxy. So the math is in our favor that the planets will actually work out, hopefully. But planets that are further out, or moons that are further out, that have a big ice layer, could also be habitats, making this number incredibly higher. But in our own solar system, to figure out whether or not there's life on icy moons like Europa and Enceladus, we have to go there, drill through the ice and look, or fly through the geysers that come out of the ice to let us probe the water below it for signatures of life. So unfortunately, for another world, for another star with a planet with an icy moon, we wouldn't be able to tell whether or not that icy moon has life. Because as soon as you invoke a huge ice layer on top that basically traps any gases that life breathes in and breathes out, and it prevents it from going to the atmosphere, at that point, I can tell you remotely, just by looking at the light, whether or not there is life on that planet. So the nice thing about this, and thanks for bringing up the moons, is actually that everything I talked to you about and all the great numbers we have is the most conservative we can go. Because there could be icy worlds, there could be moons, so it could be much more exciting still. But we're sticking to a very conservative signature for life, oxygen with a reducing gas, even so there was life before on the Earth that only produced methane or CO2, because only when I have the combination of oxygen and reducing gas can I tell the difference between life and no life. And so everything is in conservative, but because the numbers are so good, it looks like even with super conservative assumptions, we're going to have a couple of worlds that we can look at.
So oxygen is the most important gas that you can
We got.
Sorry.
Yeah.
Oxygen is the most important signature of life. So is it still possible to find life before photosynthesis was invented?
Great question. So oxygen is the most important signatures of life if it is in combination with a reducing gas. Because if it is on its own, then you can figure out geology can make oxygen. If nothing reacts with it after 4.6 billion years, you're going to have a lot of oxygen. But there's no life involved. This is why we invoke that there has to be a gas in the atmosphere that reacts with it. Therefore, if it's still there, there's huge amounts that get produced, that being life. I can say if I find a planet that has a lot of CO2 on it, ooh, that could be bacteria. Or methane, ooh, that could be bacteria. But I can't tell you for sure, because what I would need is actually the isotope ratio. And these planets are so far away that we probably, not in any foreseeable future, gonna not have enough life to actually see what the C12 to C13 ratio is to tell which one is, if it's abiotic or biotic. This other thing that we did, by looking at the colors, that can give you a clue right? So if the world were freakingly purple, we know purple bacteria, and we know what it produces. So if that all combines, the world being purple, plus the gases that we would expect in the atmosphere, we can say interesting. But we have no way of saying if not minerals could become purple too, and the CO2 could be mineral. So this is why, unfortunately, we have to go with very conservative. Another way that you could go is to say, what about civilizations? What can you do there? And there's, of course, SETI looking for radio signals, that is looking for other electrical engineers that build radio telescopes to send signals. It's probably going to be one of the only ones where nobody's going to discuss what it means if somebody says hello in a radio signal. When we find biosignatures, I promise we will just go and hammer at it and try to figure out if we can make it abiotically until we have basically gone out of options saying we only have the explanation of life. But if you go for technology, you could look for industrial gases. And one of the gases is freon that comes out of our fridges, and that destroyed our ozone hole. Good news is apparently the ozone hole is getting smaller, so we've got that going for us. But the interesting thing is, so freons, there's not much in our atmosphere, luckily, so we actually saved the ozone hole. So to see it on another planet, an industrial gas, it would have to be there in big amounts because the planets are so far away, so for me to pick it up. And then we actually have an ongoing discussion whether that means it's A, non-intelligent life because they didn't figure out they should get out of the freons. B, if it's comforting that every intelligent civilization makes the same mistake. Or C, if we use it as an anti-biomarker, that if you have that many freons, you probably subsurface or dead. Yes. It's very interesting, the discussion you get into when you think about life on other worlds.
Dave?
Water worlds are bodies that are bigger than terrestrial planets, and I guess 10 times Earth mass maybe, but covered in water. And I guess life could start there in the same way as it might start on Earth. So, given that they might be easy to study being bigger, are we going to be able to detect the biosphere on a water world as well as we could on a terrestrial planet?
Thank you very much. That was a paper I wrote a couple of years ago, so I appreciate that. Great question. I promise I'll pay him later. Envision a water world. What he was talking about is like a whole planet covered in water. What that means, really, is that you probably have no continents that go out. That's our definition of a water world. And then a lot of things change because the carbonate silicate cycle that regulates the CO2 over long times on the Earth actually needs some exposed rocks to function. Now, you submerge those rocks, it still works. But if you have a real water world, as we're thinking about it, so a bigger planet that could have more water, because if you just scale up the Earth, actually with the same mass ratio of water, water's on top, it would make a very, very deep ocean. Or you could have more heavy bombardment and bring more water in, again, a deep ocean. So if you were to dive into such a water world, it would become denser and denser and denser until it's so dense that water actually forms ice on the bottom of the ocean. That's not ice as we know it that swims on top. It's high pressure ice. It's warm still, but the pressure is just so high. And then we had to think through this because people were arguing, well, these bigger planets could be water worlds. What would that do? Because now you have a rocky core, a huge ice layer, and then water, and that's what we could detect in the biosphere. And what we figured out is that because the temperature on the bottom of the ice and on the top of the ice would be so different, the ice would actually start to convect, bringing with it some of the outgassed materials of the rock and releasing it into the water, and therefore releasing it in the atmosphere. So even for a water world, we could actually, with everything we know, find the biological signatures if there's life in that ocean. You need the convection of the ice and the bringing out the materials to seed that life in the ocean so that you didn't have just pure water. Somebody was making up this really nice thing that it would be hydrogen peroxide that would actually be in the atmosphere and everybody would be blonde. Like, probably not that great for life to get started. But a biologist that I'm working with closely was making a very nice point. We have these two theories about how life started, in the deep vents or in shallow water. And the shallow water theory is basically saying, well, both of them saying you need to concentrate the chemicals to get life started. And so in the shallow water theories, we do that actually by evaporating some of the water, and so the chemicals become more dense or become more concentrated. And he was saying you could do a similar thing on an ice sheet. If you had an ice sheet swimming on that water, you could actually recreate in principle that shallow water theory. Whether we could recreate the deep water theory, where the deep water vent actually is where the life started, where it's really hot, temperature gradient actually again makes chemical reactions more likely, that is a question, because you would have this huge ice layer in between any rocky material and any volcanic outgassing, if you want, and the liquid. So in terms of shallow water theory of how to get life started, you should be able to do that, because you can just envision something floating on the ocean and then landing it as a surface to concentrate material and also build cells. Deep water start. And what that tells you, sorry, going into details, what that tells you is that we don't know how life started on the Earth. And we really have no good way of figuring it out, because we have one data point, our own Earth, and we are not at the beginning. We can't look. We don't have a time machine. I talked about a time machine. Time machines are not possible. Sorry, should have said that too. But looking at other planets, if you found young planets that were really hot and showed sign of life, or young planets that were really cold and only those showed sign of life, or water worlds, all of them showed sign of life, or none of them did, that will tell us about this fundamental question, what it takes for life to get started and where we could look for it and how we could make it in the lab, because the parameters are huge. Another friend of mine who does origins of life research was saying it's just such a crappy PhD project. You don't know if it's 3 years or 300 years until you get the conditions right, and nobody really wants to do a PhD project that's 300 years and trying to change parameters. So the search will actually inform us of what they have to do and how life could have gotten started. But water worlds, absolutely. And the one thing why I got involved, and then stop with this answer, is that there was this amazing discovery of Kepler-62e and F, the first 2 planets small enough to be a rock in the habitable zone that was found in the Kepler mission. So the size was right, so it would be a rock, and the distance was right. And one is 40% bigger than us, and one is 60% bigger than us, the Earth. And so then the question came up, if they're bigger, they could be water worlds. But A, I wasn't allowed to talk about it for a year, what kind of sucked. But it actually, we substantiated that claim. Like we measured and measured and measured and measured. But just envision this. If you were on one of these 2 planets, they are not like Mars. They are not too small to hold on to the atmosphere and make it habitable as a second planet. You would actually have a system where you have 2 habitable planets, and one of them is really easily spottable in your night sky. I don't know if you have any better motivation than that than to get there. So I'd love to find a planet like that very close by, so that we can actually look at the atmosphere and figure out whether or not life would evolve from them, and maybe on both of those.
Other questions? I'll take chair's privilege and ask one myself, actually. There's a proposal to take the giant radio telescope, Arecibo, and instead of using it passively, to send a message actively out to known exoplanets. What do you think about that idea? Good or crazy?
Well, that actually already happened. It happened to a couple of the exoplanets. One of them was, for example, Australia Day. Then Australia National Astronomy Day, they sent a message to Gliese 581. And everybody could contribute and just basically say, you know, I have no idea if anybody would contact us back, you know, by whatever we're sending out. But it also touches on the Fermi paradox, right? Basically, where is everybody? The question comes up, if there's so many inhabited worlds, why aren't there alien among us? And no, the UFO sightings are not real. But the question that you'd ask is, if you think about the distances, so there's this cookie analogy again of our solar system and the soccer fields to get to the next star. Distances are big, and the speed of light is probably the fastest speed there is. Like, nothing has contradicted Einstein yet. So it's hard to travel. And then if they're really, that's my personal answer, if there are really that many worlds that could be inhabited out there, if I could go to only one, and I told you can pick, and one of them will be 5,000 years older than us, and one of them will be 5,000 years younger than us, which one would you pick? Who is for the younger one? Making my point. We have just started. We only have our footsteps are only on the moon. We haven't even made it to Mars with humans yet. I just think we're not that interesting. So even if we send signals out, it's going to take a while until we actually, if there's really, signals need time to travel, but it's going to be a while until I think we're going to be interesting, because even we want to look at somebody who's like more advanced, right? In a way, except for 3 people in the audience, what I find very refreshing. But I'm just explaining that way. Do you want to see a person trying to find fire, right? Actually, it's not even that yet. You actually going back even further than that. Or do you want to figure out what could come next, or how to safeguard something? I don't know. I think this whole idea of wanting to look a little bit in the future, into a possible future, is also what kind of drives us and where the communication comes from. And the problem is also, it's like we're sending radio signals, what is great. Our CB is an amazing telescope. But we ourselves are not using radio very much anymore. We're using Bluetooth, we're using cables, we're using the internet. So it could be that it's just an incredibly tiny amount of time that any civilization, first you assume that it actually goes through a radio phase. That's a huge assumption. Water worlds, I don't know if dolphins can make radio telescopes. I have no idea. I also don't know. I can't say no, but. And then you assume that this technology that in our own case only stuck around for a couple of 10 years would be the form of communication. Maybe it's something else. Maybe there's lots of interesting things out there and we're just not there yet.
Right.
Not to say that anybody in the room is uninteresting. That was not what I meant.
Any other questions? No? In which case, let's thank Lisa once again.
Thank you.
So it falls to me as head of astronomy to say just a few closing words. Astronomy at the OU has gone from strength to strength, but this has only been possible because we have been building on the achievements of the previous research leaders. So Barrie led the Department of Physics from 1999 and saw the creation of Physics and Astronomy Department and set us on a very secure research path, and along with Russ and other departmental heads, set a very friendly and collegial tone, which persists to this day, and to me is one of the nicest things about working at the Open University. Now, I'd like to thank Lisa again for a fabulous talk, and I'm going off piece now. I think Barrie would have loved that. He would really have loved that, and it's great to be in such a tremendous time of discovery in this area. It's thrilling. And this talk will be available online soon, so watch this space. And I'd also like to thank the Astrobiology Society of Britain and the Open University for supporting this new award. And it only remains to wish you a safe journey back to wherever you've come from, and thank you once again. Thank you.